So here we go. It is Tuesday, December 1st, 2020. It's, as far as I'm concerned, the official start of the holiday season. We're in December. We're going to be covering section 5.3 this week and next week. That's conditional probability and independence. Right, today we'll be focusing on conditional probability and what that is. Looking at a couple of examples. If you're taking notes, you probably want to have some of those ready. Before we get into our new content, there's a couple of things that I noticed over the course of grading over the last week. A couple of things that really stood out as common errors or common misconceptions that I wanted to address. All right, first, in the assignment, table A is your new friend. I know this wasn't a very new assignment, but it's one that I did more grading on. And I saw a very, very, very common mistake. I'd say about 90% of the students who submitted responses for this discussion board got question 2 wrong. And that's in the feedback that I provided. However, it is not because you used poor technique or poor strategy. It's that you missed the last step, right? One thing that's going to be very helpful when dealing with z-scores, right, and finding proportional observations using an standard normal distribution is having the picture, right? It doesn't have to be perfect. It could just be a sketch, but having a picture of what you're doing is going to be incredibly helpful. Many of you found the solution, right, for the proportion of observations when z is greater than negative 2.15 to be 0.0152, all right, or 1.8, sorry, that should be an 8%, okay? And this is because when you looked on table A, right, this is the value that you found, right? So if we look at this sketch, right, we have the middle here is going to be mu. We have 1 standard deviation, 2 standard deviations, 3, -1, -3, and then we'll have like right here, we'll call this negative 2.15. This is the z-score we were looking for in the distribution. The value on table A that shows up with negative 2.15 for a z-score is the proportion under the curve less than 2.15, right? Which means this portion represents 1.58% of the distribution. That's unfortunately not the proportion we needed. We needed to the right, greater than, right? We were looking for this whole thing here, right? This was the area we were looking for. Now, if we draw the picture and we look at this, it's easier to see that this should be obviously a large percentage or a large proportion. The step that you're missing is when we have a sign flipped over here where it says z is greater than. We take that z-score, find this value, and then subtract it from 1. Right? So the correct observation, or the correct proportion of observations would be 1 minus 0.0158, which is equal to 0.9842. 98.42%. Right, so most of you got this far. You need to take one more step, right? And that is just realizing that we're looking for to the right of that answer instead of to the left. Table A always gives you the proportion to the left of the value you're looking at, right? Is there anything else I can clarify for this example? All right. So then on our next thing here, probability models and basic rules. This is more recent. The difference between A or B and A and B. All right. This is a major thing in mathematics, in probability, in set theory, and lots of other areas of mathematics where there's the verbiage and or being used. In these areas of math, or is inclusive. When you're between two things, one set and another set, one event and another event, and the word or is connecting them, that means you can be in one or the other, and you've satisfied the statement. It is true. It is good to go. All right. In an or statement, right, or a union, to satisfy the statement, one or both of the events need to occur. If we're talking about probability, the one or the other is fine. You don't need both. They both don't need to happen simultaneously. You just need to have one or the other occur. You've satisfied or. When we're looking at and, that's more restrictive. That's exclusive, right? In an and statement or intersection, to satisfy the statement, both of the events must occur, right? Both parts, both things must be satisfied to be a part of that event and to be counted in that situation. And that's the major difference between and or. Right? In this discussion board, almost everyone who responded to the discussion board got the first part correct, saying, yes, these events are mutually exclusive because you can't have both things happen at the same time. And then when you're asked to find the probability of either or happening, some of you didn't find it. Some of you said it was impossible because they're mutually exclusive. It would only be impossible if we were looking for the and condition. A and B happening at the same time, we know that that is not possible. That has a probability of 0. But for A or B to happen, just one of the two things needs to happen, so we get a larger set of possible things that work. Okay. And we also have our new notation for union. We have A union B, intersection, we can have A intersection B. And I can remember these because the union, this symbol, looks like a U, and the intersection symbol looks kind of like an A. That's how A for and, U for union. That's how I remember. Okay. Anything else I can clarify about the difference between an or statement and an and statement? Cool. Then we're going to jump into the new stuff. So, conditional probability. What is conditional probability? Conditional probability piggybacks off the concept of conditional distributions that we have previously seen with categorical data. Right? We are adding another thing that we can do with conditional distributions, right? Our two-way table. We've already seen these things. We can fill in the numbers. We can get the totals. We can show a distribution in that. So now this is the next thing, is talking about the probability of things occurring. Conditional probability is finding the probability of one event under the condition that some other event is already known to have occurred. Conditional event is often referred to as the given event. You'll see that term used sometimes in these. We will say, it is given that blah, blah, blah. What is the probability that this other thing happens? Or could we say, it is known that something happens. What's the probability that this other thing happens? Right, so you're given some condition that's already occurred. And based on knowing that that's happened, what's the probability that something else also happens? Right, that's what our conditional probability is looking at. So for example, if we're being asked to find the probability that a student is female, given that the student is taking AP Stats, right, The conditional event is the student is taking AP Stats. We know that the only set of students I need to look at right now are students taking AP Stats. And of those students, we want to know what's the probability that the student is female. So when I have a conditional probability, I get to narrow down the population that I'm looking at based on the condition. So rather than looking at the entire population, I get to look at a smaller portion because that's the only thing I need to consider. That's the condition. So anything I can clarify or explain in better detail? Does anyone need a moment to write anything down from this slide for their notes? All right. So in a previous example that we looked at before break, we looked at an example where a large college statistics class collected data about gender and whether or not the students in the class had pierced ears. There are 178 students in this class, and here is that data once again. So we have this two-way table between pierced ears and gender. In the previous example, we used two events. Event A was that the student was male. Event B was that the student has pierced ears. Right? And we found these results previously. When we looked at that example, we know the probability that a student selected from this class is male. We have 90 male students out of 178. We can look at the probability that a student selected randomly from this class has pierced ears. That's 103 out of 178. We can look at the probability that a student selected at random from this class is male and has pierced ears. Right? That's a smaller number. We have 19 possible students out of 178. And then we can also say, okay, what's the probability that a randomly selected student is male or they have pierced ears? That creates a larger set of possibilities. Can be male or have pierced ears. In this case, this union of male and pierced ears, we need to make sure to subtract the things that are counted twice, which would be males with pierced ears. So remember, we added 103 to 190, or 103 to 90. We got 193 and had to subtract 19. That left us with 174. Got to be careful with double counting. All right. So you need any extra explanation on how we came to these results here for these four probabilities? So now, let's look at a couple of new questions based on a conditional probability. Question number 1. If we know that a randomly selected student has pierced ears, what is the probability that the student is male? So again, we have the same two events occurring in this statement. We have student has pierced ears, and the student is male, right? Student being male is event A from our previous example, and this is event B. To properly move forward in this example, we need to know which statement is conditional. Which one is the given information that we know has already occurred? Event A or event B? And that way we can correctly identify the conditional set of data we're going to use. If we don't do that first, we're going to have a hard time. So, what do you guys think? Which statement, A or B, is the given information or the conditional event? You just type what you think in the chat. A or B? Got a 50% chance of getting it right. All right, we got B. Who else, guys? Come on. This is like no risk, opportunity, give it a shot. We've got 2 students who believe it is B. So Lally thinks it's B as well, all right? All right. So Joanna, Esmeralda, Lally, and Fernando, you are correct. Statement B is the given information. That is what we know. It says, if we know that a randomly selected student has pierced ears, so we've selected someone who has pierced ears. We already know that. That is given information. Right? What are the chances that that student who has pierced ears is male? Right? So we want to find out P of A given B. Written as like kind of a statement here. We'll get to the notation next. So what's the probability that event A happens given that B has already occurred? So we've already picked the student and we know the student has pierced ears. So that means the only set of data I need to look at is the students with pierced ears. I don't need to worry about the other students who don't have pierced ears. I know I'm only looking at someone with pierced ears. So of those students, what's the chances or what's the probability that they are male? We only have 19 male students with pierced ears. So we have a probability of 19 out of 103. Right? So instead of it being a probability out of 178 out of the entire class, we now only need to consider the 103 students with pierced ears. Right? So then on question 2, we now know that a randomly selected student is male. Right? This is event A. And we want to know what is the probability that the student has pierced ears. Event B. In this case, we've swapped, and now event A is given. This is the known information. We've selected a student. We know that the student is male. What is the probability that the student has pierced ears? This is slightly different. We have what is the probability of B given A. So now the condition says only look at male students. And of those male students, I want to know what's the probability that they have pierced ears. Again, we end up with that 19, but now it's 19 out of 90. Because I'm only considering the 90 male students. Okay, so the conditional probability, it's not fixed on like a row of data or a column of data every time. You need to infer that from the statement. What's your given? The given information tells you which set of data to identify first. Are there any questions? Anything I can clarify or make better sense of for you? Does anyone need a moment to write anything down from this example? All right, so this leads us to our textbook definition of conditional probability. This is the probability that one event happens given that another event is already known to have happened is called a conditional probability. Suppose we know that event A has happened. Then the probability that event B happens given that event A has happened is denoted by P of B given A. This little bar, up and down bar, this essentially takes the place of the word given. So what's the probability of B given A is what this notation represents. In this notation, the given event is always listed second. Right? A is the given event. And it's the way that you read it. B given A. Right? The order in which these are written matters. The probability of B given A is not equal, or not always equal, to the probability of A given B. They can be equal at times, but they're typically not. So the order in which you list those variables matters. And we just saw this on the example, right? The probability of B given A was not the same as the probability of A given B. But this is our new notation. You're going to want to know what this means when you see it. Right? That little bar. We're talking about probability. Okay. And we need a moment to write any of this down. Then as like a backtrack to go back into the new notation, this looks at the work that we already did and kind of the math behind what we did. For the example, we have the probability that a student is male given that we know the student has pierced ears. Right? That is the fraction number of students who are male and have pierced ears. So we have an and statement at work here. That's 19. That's the intersection here. Divided by the number of students with pierced ears. Right, the 103. Right, and that's obviously what we found. We can also focus on probabilities instead of numbers. Right? It's entirely possible that you will be given a situation where you don't have the two-way table. All you have is the proportion or probabilities. You don't know what the actual numbers or counts of each thing are. So you need to be able to make sense of it if all you have are the proportions. Right? So in this case, we have the probability of male and pierced ears, right? Same thing that's in the numerator here, divided by probability that someone has pierced ears. Same thing again. But these are previous results that we already had. Right? We knew that the probability of male and pierced ears is 19 out of 178. The probability of having pierced ears is 103 out of 178. Right? This reduces down to 19 out of 103. The 178 on the top and the bottom basically cancel out because they're in the top and the bottom of the fraction that's actually being divided. Right? And so we get the same result. This is comforting. We should get the same result. It means that math works. It has not failed. Right? In symbols, the probability of A given B equals the probability of A and B divided by the probability of B. This leads to the general formula, which is on the next page. Is there anything I can clarify about this set of math on this page? We don't need a moment to write anything down from this page. So then these are our general formulas. Right? To find the conditional probability of A given B, we use the formula probability of A given B is equal to the probability A and B, or A intersection B, divided by the probability of B. If we have that flipped, to find the conditional probability of B given A is the formula probability of B given A equals probability of B intersection A divided by probability of A. Something to notice is that the thing that is given, right, the event B here, is the event whose probability goes into the denominator spot by itself. All right. Same thing here. All right. If this is one scenario we're talking about, the probability of A intersection B should be the same as the probability of B intersection A. So you don't need to find two different numbers for that. Those things, what is that? They commute. I believe that's right. Yeah. All right. So any questions on these formulas? We know and have they're very helpful. We'll use them. Okay. All right. Does anyone need a moment to write any of this down for their notes? All right, last example. So we're given this scenario. And in this scenario, we have essentially a Venn diagram showing the proportion of people who read USA Today, people who read New York Times, and people who read both. And over here, this 0.4 here, that is the people who don't read either. It's the complement. So our problem is, what is the probability that a randomly selected resident who reads USA Today also reads the New York Times? Based on our context, reads USA Today is event A, reads New York Times is event B. The way this is written, we are told that the resident selected reads USA Today. Right? So this event A is given. We know event A has already occurred. Something else useful is let's just have our probabilities here. All right. These are the three possible probabilities we might need. Probability of A, probability of B, probability of A intersection B. Based on this Venn diagram, can someone tell me what is the probability of event A? That someone reads USA Today. All right, so what we is saying is 0.35. All right. So now, I'm going to draw a circle here around the circle that represents event A. Right, that red circle represents everyone who reads USA Today. All right. The part of the proportion that is not automatically counted right now is the 0.05 that read both. Those people read USA Today, so if I'm looking at the probability that someone reads USA Today, I need to include that 0.05 into the 0.35. Right? That is everyone who reads USA Today. So we have to add these up, and we get 0.4. And this is why I picked this example, because you'll see examples like this that are kind of purposely misleading. Okay, this 0.05 belongs to this, the USA Today, and it also belongs to the New York Times. So the probability of B is 0.25. Right? Which then, right, A and B, the intersection, is that 0.05. Do you guys see how we have to like make a small adjustment here to account for the proper proportions? You guys understand why I'm adding the 0.05 back into both of those? I hope so. All right. So let's look at the actual problem. So now we need to find out what's the probability of B given A. In this, using our new stuff, we have probability of A and B divided by the probability of A. This is the formula that we just saw on the previous slide. We do not have the count of what happens. We can't use those proportions. We just have to use these decimal proportions that were given. Right. Probability of A intersection B, which is the same as probability of B intersection A, is 0.05. Probability of A is 0.4. And this will give us 0.125, or 12.5%. What can I clarify? What questions do you have about this process? No questions? You guys are awfully quiet today. We don't need to write anything down from this example. So then, at the end of the slideshow, I'm going to look at the discussion board for today, which is the conditional probability of grades. Right. So here's our context. We have students at the University of New Harmony received 10,000 course grades last semester. The 2A table below breaks down these grades by which school of the university taught the course. The schools are liberal arts, engineering and physical sciences, and health and human services. Right. And so then we have the 2A table here between school and grade level, A, B, or below B, liberal arts, engineering, health. College grades tend to be lower in engineering and physical sciences, which they're labeling as EPS, than in liberal arts and social sciences, which include health and human services. Choose a University of New Harmony course grade at random. So think of all 10,000 of these grades, been dumped into a hat. And on like each piece of paper, it says the grade and the school that the grade came from. All right, we're going to consider two events. Event E, the grade comes from an EPS course, and L, the grade is lower than a B. All right. So what's the probability that a grade is lower than a B? Right. This is not a conditional one. This is just find the probability. And then interpret this probability in context. What does it mean? Right. Second question, find the probability that the grade comes from an EPS course given the grade is lower than a B. And find the probability that the grade is lower than a B given that it is from an EPS course. Okay, so you're going to have to use the values on this two-way table to find those probabilities. The last part of question 2, which of these conditional probabilities tells you whether this college's EPS students tend to earn lower grades than students in liberal arts and social sciences? Explain. It doesn't need to be a huge explanation. 1 or 2 sentences will suffice.